Hi guys, this is part 2 of a two-part series of videos on the 2014 VCAA Specialist Maths Exam 2 Extended Response questions, and in this video I'll be dealing with questions 4 and 5. Now remember, these are just my unofficial solutions, So let's go with this and see what we can find out. Question 4, we've got the dreaded conical tank question, related rates for sure, and these are always very much fun, and I find them very easy. Hope you do too after I show you how. Conical tank radius 0.5 meters, height 1 meter, okay, get that, is filling with water. At the same time, some water flows out from the vertex, which means the bottom part, the pointy bit, wetting those underneath. When the tank eventually fills, it tips over and the water falls out, goodness, drenching all those underneath. Okay, how thrilling. The tank then returns to its original position and begins to refill. Okay, well, we think we sort of get that. That's 1 meter, that's 0.5 meters. That's the height h at any time. Okay, so water flows in at the constant rate of 0.02 pi meters cubed every minute, flows out at the variable rate of 0.01 pi root h. Cubic meters per minute, where h is the depth of the thing at any time. Alright, we get that. Show that the volume V cubic meters of water in the tank when it is filled to a height of, to a depth of h meters is given by that thing. Well, that's just straight geometry, isn't it? That's just straight geometry. We can do that. We can do that if we know about similar triangles. That's the point, guys. These always involve similar triangles. So let's just put some information in here. That's the in rate, that's the out rate, which depends on the height, okay? So, by similar triangles, okay, you've always got to look at these similar triangles. You've got to look at the big one, this one which has a length there of 0.5 and a height there of 1, and then look at this little one involving the instantaneous situation here, this one and this one, because they will have the same proportions as these big ones, AB and AC. So we know that by similar triangles, AB over AC, so that's in the big triangle, AB, horizontal over vertical, equals the same situation in this small triangle, DE over DC. Because they are similar, you never have to prove they're similar, but I can show you why they're similar. We have a common angle here in both triangles. We have a common, well, we're not in common, we have a right angle here and a right angle there, so therefore, if 2 corresponding angles out of 3 are the same, then the third must be the same. This one and this one, therefore they are similar, and the rule is AAA. They are equiangular, okay? But don't worry about that, you don't have to prove it. Alright, so therefore we know that a half over 1 equals R over H, therefore that gives us a connection between R and H, which we need. So therefore R is H over 2. Alright, now let's go just to the straight geometry now and get the volume of a cone, which has a height of h. Okay, so V water equals 1/3 times pi times r squared times h, which is the volume of a cone. And what we've got to do, because this thing only involves h, we've got to get the connection between r and h, and happily we have it. So there it is. So let's just substitute for r in terms of h, and we get that. Now, hopefully that's going to work out to what they had down here. I'm sure it will. Yes, it does. Beautiful! We've done it for 1 mark, alright? Great. Okay, let's do part B now. Find the rate in meters per minute at which the depth of the water in the tank is increasing when the depth is 0.25 of a metre. So we've got to find dH dt, don't we, guys? Yes, dH dt. So look, let's get our ducks in a row here and write out what we know. We know that dV dt is the rate in minus the rate out. That's the first thing. And then also by the chain rule, we also know that V is this thing, because that's what we found out in part A. As the story unfolds, we're going to need that for dV dH. I'll show you in a moment. Then by the chain rule, we know this. This is really important. dV dt equals dV dH times dH dt, and we've got to find out dH dt. Okay? So we know that. We don't quite yet know that, but we'll know it in a jiffy once we do the derivative of this here, up here, dV dH, okay? And so it'll be easy, it'll be a snap. So therefore dV dH from this equation here is just going to be 3 times h squared times pi over 12, which gets us pi h squared over 4. Okay, now we're nearly there now, guys. We substitute into the star equation up here, and what do we get? We get dv dt, which is this thing here, equals dv dh, which is what we just got there, times dh dt, and it's easy for us to get dh dt. Very easy. Cancel those pi's, and what do we get? Right, we get that, don't we? Have a look at it, see if you agree. I've just done a few little changes there. 0.02 minus 0.01, I've just called that 200ths minus 100th. Then we get that there, and we're multiplying both sides by 4 over h squared. That leaves this little baby by himself on the right hand side, which is what we want, isn't it? Now all we've got to do now, guys, is substitute that h is a quarter in there, and happily it'll all work out. There it goes. Just be careful, don't muck it up. See what I've done. Yes, that's the square root of a quarter, isn't it? And that's a quarter squared. It's looking good. So therefore we're going to get that. Yes, after a little bit of manipulation throughout the nation. And then we're going to get that. And that's going to be that. 0.96 metres per minute. Now that's exact, right? They didn't say to any decimal places or anything, so that's exact. So we've done it. We've done it. Alright, over the screen now. The tank is empty at time t equals 0 minutes, and then in part C we've got to, by using an appropriate definite integral, find the time it takes for the tank to fill. Give your answer in minutes, correct to 1 decimal place. So we don't need the exact answer here, guys, and it's worth 2 marks. Well, as the story unfolds, as I was saying, in the previous part of the question we got dh dt was that. So now all we've got to do is solve that for t. So we need to do the old flipperoonie after we simplify that a little bit, and we'll get that. And now we've got to integrate, and we've got to solve it for t, where h is going to be going from 0 to 1, because the cone was 1 metre high, and we're going to get that. Now, don't stress, don't worry. You're looking at that thinking, heavens, how am I ever going to work that out? Don't worry, you don't have to. The calculator does it. You see, look, correct to 1 decimal place. That's all you need. So just get the old Kaz on the job. And what do you get now? 1 decimal place. So 7.4 minutes. 7.4 minutes to 1 decimal place. Yes, looking good. Alright, over the screen we go. And what have we got here? Goodness, this looks interesting. Another water tank shown below has the shape of a large bucket, which is part of a cone, e.g. a truncated cone. With the dimensions given, alright, so what have we got? 1 metre, 0.75 there and 0.5 there, alright. Water fills the tank at 0.05 pi metres cubed per minute, but no water leaks out, alright. Now, when the thing is filled to a depth of x metres now, the volume of water V, cubic metres, in the tank is given by that, alright, that's V as a function of height. Given that the tank is initially empty, find the depth x as a function of time t. 5 marks, right, so this is going to be a bit of a marathon. But I think it's exactly the same procedure as what we did before. If we can get dx dt, using the chain rule and all the rest of that stuff, then we could solve it for x in terms of t, I would think, without too much trouble. As long as we keep our heads and make sure we're careful with what we're doing, we'll be fine, I think. So we know that dv dt is that, don't we? That's a given. We know that that's our star equation. This time we're using x for height, but now we'll sub in what we know. So therefore, we know that v is this function of x, so we can get dv dx because we need that for the star equation. You see, so we'll do that. We've got that. So we've got that. Now I'm just simplifying that a little bit, and then I'm oh yes, look at that, nice. That's a perfect square. So we've got that, okay, dv dx, alright? So now, we're going to put that into the star equation like we always do, don't we? And we're going to get this. So 0.05 pi is pi over 20, just to make that a bit simpler, and we've got that there, and we've got that. So basically, we want dx dt, guys. So we're going to cancel those pi's and cancel that there, and we get this, dx dt is equal to that. Alright, now let's have a good look at that. That's in terms of x. So we'll have to solve that, we'll have to do the old flipperoonie trick and get the t dx and solve it for t and then make x the subject would be my guess. So let's go with that. That looks good, doesn't it? Solving that for t, yes. Oh, that's nice and easy, isn't it? No problem. So that's going to be that. Now we've got to sub in our boundary conditions. We know that x is 0 when t is 0. So therefore, what are we going to get out of that? It looks like c is minus 10 over 3. Okay, goodness me, Mr. C. So therefore we get that. Now all we've got to do now, ladies and gentlemen, is solve that for x, make x the subject, which will take a little bit of messing around, but that's alright, it's worth 5 marks, we don't mind. So let's do that, shall we? Over the screen. Now off we go, that's a recap. Now make Mr. X the subject. So we'll add 10 over 3 to both sides and then multiply by 12 over 5. I've done 2 steps in one. Alright, you agree? Alright, good. Now we're going to cube root both sides. We're getting that, and now we've got to subtract 2 from both sides, and we get that, and that's our answer. It looks pretty monstrous, doesn't it? But it's looking pretty good for 5 marks, I would say. Alright, let's do question 5 now. Alright, it looks like we've got an inclined plane problem here with connected masses all over the place. So let's see. The diagram shows blocks of mass 3 kilograms, 5 kilograms on a smooth plane, so no friction, of inclination theta degrees to the horizontal. They're not giving us the value, it's just theta, connected by a taut, light, inextensible rope. The 5 kilogram block, which is this one, is connected by another light, inextensible rope via a smooth pulley at the top of the inclined plane to a block of mass 2 kilograms, this baby here, hanging vertically. The 2 kilogram block has an acceleration upwards of a meters per second squared, alright? Okay, we get that. The forces on each of the 3 blocks are shown in the diagram, alright? Very nice. Write an equation of motion for the 2 kilogram block for 1 mark. Goodness, that's so easy. That's just going to be T1 minus 2G equals 2A. Hooray today. Excellent job. Okay, onwards, ever onwards, guys. So what's this? By resolving forces acting parallel to the plane on the other 2 blocks, write down an equation of motion for each of the 3 and the 5 kilogram blocks using the symbols defined in the above diagram. Alright? This looks like another nice easy question for 2 marks, guys. Now what I'd like to do with these questions is I label the positions. So let me call that 1, position 1, and this position 2. Just makes it easy to explain what I'm doing. So therefore at 1, now remember that the motion is this away, going that away, because this block here is going upwards, so obviously these are going that way down the plane. So at position 1, we've got the horizontal or the parallel component parallel to the plane of this gravitational force 3G minus this tension will equal 3A. So we've got 3G sine theta, remembering that this angle here, if I draw that line perpendicular to the plane that way, then this little angle in here between that line that I've just drawn there, that perpendicular line, and this force will be theta. Okay, so 3G sine theta minus 2 equals 3A. That's no problem. And I call that equation 2 because I've already got an equation over the page which I called equation 1 on the previous screen. And therefore at 2 we have T2 minus, right, what's going on here, minus this parallel component of the gravitational force on this one, which is 5G sine theta minus T1 equals 5A. That's it. Put a box around it, and that's 2 marks for us. Terrific. We're cruising. Now, what have we got to do here? Well, we have to show that A is equal to this thing here. Alright, now, we need our 3 equations, guys, and there they are. Now, at first glance, this looks really troublesome because we've got, we're trying to solve for A, but we've got T1s and T2s sprinkled all over the place in here. But if you just keep your head, which is really what you've got to do in an exam setting, realising it's only a 1 mark question, it can't be that hard. So if you just have a look at it, think about this. You could get yourself involved in a great big simultaneous equation trauma, or you could realise, if you're not too stressed, that just by adding all these three equations up, all three of them, you'll notice that the T1s and the T2s mercifully cancel each other out. You see, there's a T1 here and a minus T1 there. There's a T2 here and there's a minus T2 there. So if you add all three equations up, you'll just be left with dear old Mr. A here from the right hand side, together with some G terms over here. So let's do that. And we get that. Goodness gracious, isn't that wonderful? So you get 8G sine theta minus 2G equals 2 plus 3 plus 5 is 10A. It's very easy. Let's just divide both sides by 10 and you get that, and then you just do a bit of cancellation throughout the nation and you get that, which is the answer as required. Isn't that beautiful? So let's go on. Alright, now we're considering a different situation where the 3 kilogram and the 5 kilogram blocks are placed at rest on a rough plane. So now we've got friction, guys. The plane is inclined at 30 degrees, so theta equals 30 now, 30 degrees to the horizontal, a tangible value for the angle, and as shown. And there are no strings, oh goodness, there's no strings in here attached to the two blocks. Alright. The coefficient of friction between the 3 kilogram block and the plane is 0.11, there, and the coefficient of friction between the 5 kilogram block and the plane is 0.01. Oh, goodness. Initially, the distance between the two closest faces of the blocks is 3 meters, as shown here. Well, that's very interesting. Because this has got a coefficient of 0.11 and this has got a coefficient of 0.01, that tells me that this is a rougher situation here than this one, which means that this one is going to come down the plane faster than this one. So this one's going to be sort of catching up to that one. Anyway, that's not what we're asked for, but that's just what I'm observing, because that's probably going to be important later on. So what we're doing here, meanwhile back at the ranch, is on the diagram below, show and label the forces acting on each of the two blocks. Yes, that's alright, we can just do that. So what have we got here? We've got 3G gravitational, we've got N1, the normal to the plane at position 1, and we've got friction force 1, right? Same thing over here, we've got 5G gravitational, we've got the normal N2, normal force here, acting on the 5 kilogram block, and then we've got the friction force 2. So that's 2 marks we got for that question. No problem. Over the screen we go. Calculate the acceleration of each block down the plane. Give your answers in meters per second squared, correct to the nearest 0.01 meter per second squared. And you can see where this is leading, guys. Once we work out the acceleration of each body, one will be accelerating more than the other, and they'll be probably asking us to work out how long it takes for one to catch up to the other. And we'll just see, though, as the question progresses. There's our forces, so let's just go through the motions here. What have we got? At point 1, we've got that. Okay, so we've got 3G sine 30 minus 0.11 times 3G cos 30, which that bit there is the normal force, because we've got mu n. That's the friction force, is mu n, where mu in this case is 0.11. And that equals 3A, so we've got to solve that for A for that block, the 3 kilogram block. So let's just do that. And as we go through the motions, we get all this, and then we get 3.97. That's to the nearest 0.01. Yes. Now we do the same thing, same process for point 2, the 5 kilogram block. We get 5G sine 30 minus 0.01 times 5G cos 30 equals 5A. Solving that for A for the 5 kilogram block, we'll get all that. 4.82 meters per second, which is accelerating faster. That's what I was thinking, than this beastie down here. Yeah. So all right. So we've done that. That's 2 marks for us. Now let's have the next question. Calculate the time taken for the 5 kilogram block, I told you, didn't I, to collide with the 3 kilogram block. Give your answer in seconds, correct to the nearest 0.01 second. And this question's worth 3 marks. Now many students will just throw their hands up in the air and say, we weren't taught this at school, so we can't do it, and they will give up. But look guys, remember the Wolfie motto. The answer is never very far away. So just think about it. Just think about it. Just Imagine a situation in outer space, for example, where everything else is blacked out and all you can see is two blocks, okay? And if you're sitting on the first block, looking backwards at the second block, what do you see? You see a block which is accelerating towards you with a net or relative acceleration, which is the difference between the 5 kilogram block acceleration and the 3 kilogram block acceleration. That's the rate of acceleration which you observe that 5 kilogram block coming towards you with. And that's how you solve this question. It's relative acceleration. So the acceleration of the 3 kilogram block is 3.97 meters per second squared, yes. The acceleration of the 5 kilogram block was 4.82 meters per second squared, and the relative acceleration between the two blocks, as I say, if you were sitting on that first block, you would see the second block accelerating towards you at 0.85 meters per second squared, closing that 3 meter gap as time progresses. And all you've got to work out is the time it takes to close that 3 meter gap when it's accelerating towards you with a relative acceleration relative to you of that. Okay? So therefore we can just use the old constant acceleration formulas. X equals ut plus a half at squared, where x is 3, u is 0, and a is 0.85 relative, guys. And it's just as easy as that. So we've got 3 is a half at squared because u, the relative u, was 0 of the block that's catching up to the rear block that's catching up to the front block. Okay, that's the 5 kilogram block catching up with the 3 kilogram block. This relative initial velocity is 0, so we've just got 3 equals a half times a times t squared. All we've got to do is solve that for t, and we're laughing, guys. We're laughing. So t is that, and if you work it out to the nearest 0.01 second, you get that 2.66 seconds to the nearest 0.01 second, and that's your answer. And that is the end of the paper. Alright, and I hope you got something out of it, and we'll see you anon. All the best.